Hello, my name is Louis Mantini, and I'll be hosting today's webinar. I work for the Swanee River Water Management District in Live Oak, Florida, and I have been with the webinar committee since 2017. Topic of today's lecture will be constructed wetlands for wastewater treatment, types, and use for various wastewaters. It is our pleasure to introduce our speaker, Professor Jan Vymazal. Dr. Vymazal graduated from the Institute of Chemical Technology in Prague, Czechoslovakia Republic in 1980 and received a PhD from the Institute in 1985. Between 1985 and 1991, he was affiliated with the Water Research Institute in Prague at the Department of Wastewater Management, or Treatment, excuse me. In 1991, Jan joined the Duke University Wetlands Center in North Carolina as a visiting scholar. During his stay at Duke and until 1993, he focused on the wetland plant communities in the Florida Everglades. From there, Jan worked as a freelance researcher, focusing mostly on constructed wetlands for wastewater treatment. In 2007, he joined the faculty of environmental scientists at the Czech University of Life Sciences in Prague. He currently is the lead of the Department of Applied Ecology and Vice Rector for Research and Science. Jan has authored more than 160 papers, indexed in Web Sciences with over 10,500 citations and an H-index of 46. He wrote 2 books and edited 9 books on natural and constructed wetlands, and he is the editor-in-chief of the journal Ecological Engineering. Thank you, Jan, for joining us, and I'll let you take over from here.
Thank you very much for the introduction, and good afternoon or good morning or good evening or wherever you are. And my talk today will focus on the use of constructed wetlands to remove nutrients from agriculture drainage. The agricultural drainage pollution is worldwide, and it causes a lot of problems. But most difficult is the problem of eutrophication, as agricultural drainage trigger eutrophication of streams. This is a small drainage ditch in the Czech Republic with a large amount of filamentous algae.
Jan, can you share your screen for us? Can you share your screen for us?
Yes, it's try to. Yes, this is.
Thank you, and you just have to unmute yourself.
So now it should be okay.
Yes, looks good.
I
Thank
guess.
you.
So I just returned one step back. So I said that the nutrients from agricultural drainage, they support eutrophication of streams as well as water reservoirs, but also coastal areas. And so agriculture, especially tile drainage, is a big problem. It has been found as early as in 1970s that natural wetlands has the ability to retain and transform nutrients. And it was also recognized that the major processes responsible for nitrogen removal in wetlands are denitrification, plant uptake with the subsequent harvest, because if we don't harvest the plants die back and release the nutrients back into water. There is some sedimentation, sediment accretion, and volatilization of ammonia. As far as the phosphorus is concerned, so the major processes responsible for phosphorus retention in wetlands are sedimentation and sedimentation accretion, plant uptake, again with subsequent harvest, sorption is quite important, and precipitation and co-precipitation. There is quite a difference between retention of nitrogen and phosphorus in terms of processes, because most processes responsible for nitrogen removal are microbiological. However, major processes responsible for phosphorus retention are chemical or physical chemicals. There were some principles given by Bill Mitch in 1992. This paper appeared in the very first issue of Journal Ecological Engineering in 1992, which was released during the Intercol Wetland Conference at Ohio State in Columbus. And he set up some basic rules which should be used for constructed wetlands for removal of pollution from agricultural drainage. So the system should have minimum maintenance. They should use a natural energy, so that means they should not use electric power, which of course will be very difficult in the middle of the fields. This should be designed with the landscape, not against it. That means that it should fit in the landscape. They also be good to be designed with multiple objectives. So the treatment or removal of nutrients should not be the only objective. For example, it could be a bird habitat or increase the biodiversity. It should be designed as system ecotone, which wetlands usually are. That's the ecotone is a site where two different ecosystem meets. That means the terrestrial and aquatic. We should give the system time to develop. That means that we should not expect immediately a very high performance, even though wetlands usually do so quite early. It should be designed for function, not for form, and they should not be over-engineered. So that means that it should be really fitting in the landscape and not using the rectangular bases or some concrete structures and so on. There have also always been the debate, and I think it's still the open question, where these wetlands should be placed. Of course, there are several options. They could be, we can use the smaller wetlands upstream. That means to catch the pollution from the upper reaches, or we can create some large wetland downstream, or there are some other options. We can build it in the stream, or we can build it upstream. So there are many options. And of course, and I will show you some examples from the Czech Republic in my presentation, that there are different options how we can use these constructed wetlands or semi-constructed wetlands for controlling of the pollution of this type. There are several basic types of constructed wetlands. Those are with surface flow. That means that there is water on the surface. The water is usually shallow, and the ponds are very densely planted with vegetation, various types, with emergent vegetations like typha, cattail, Phragmites. Of course, in Europe, we use quite often Phragmites australis. It's not so popular in the United States. but there are some other species like carex or Cirrus. And then there are two major types of horizontal of subsurface flow, and we can have either horizontal flow, where the water flows more or less horizontally below the surface of the filtration bed, and with the principle of connected vessels, we can maintain the water level in the bed. And we have the vertical flow, that the typical vertical flow has the inflow at the surface. And what is important to say that in a typical vertical flow constructed wetlands, the water is fed intermittently. That means that we feed the wetland for a short period of time, then we let the water percolate. It means that the filtration bed is empty for a certain period of time, which allows for air and oxygen diffusion into the filtration bed. And this system is predominantly aerobic, while horizontal subsurface flow systems, because they are all the time submerged, they are usually anoxic or sometimes even anaerobic. Recently, there is one type, which is usually called floating islands or floating treatment wetlands, because it's been found, and it's known for a long time, that some plants, these emergent plants, which usually root in the sediment, can float. And so we create some light structures which keep the plants floating, and so we don't need to use a filtration material, but we can let the plants flow on the surface. Of course, if we are using free water surface constructed wetlands, there are 4 major types of plants we can use. Emergent plants, which root in the sediment, grow through the water column and above. I would say the typical plant is probably Typha, or in Europe, Phragmites australis. Then we have free floating plants. Those are, I think, the most common plants are water hyacinth and duckweeds. However, these systems need to be very frequently and very often harvested, because the plants grow very fast, and in order to allow them to grow, we need to harvest them. And actually, there is not much use for the biomass at the moment. So the operation and maintenance of these systems is relatively expensive. Then we have some submerged plants, which grow only in the water column. And the last group are water lilies type plants, which root in the sediment, and the leaves are floating on the surface. A few examples. I think that one of the most well-known constructed wetlands for agriculture runoff are the stormwater treatment areas in Florida Everglades. So as you may know, during the 20th century, about 1/3 of the former Everglades in the north were drained and converted mostly into sugarcane fields, which are very heavily fertilized, and the runoff, especially phosphorus, causes a lot of eutrophication in the so-called water conservation areas and even in the Everglades National Park. So they are very large, these STAs. At the moment, there are 6 of those. There are more than 10,000 hectares, mostly with floating macrophytes fixing the phosphorus. This is the typical picture from the South Florida. So those are former Everglades converted into sugarcane fields, causing a lot of eutrophication with increased phosphorus concentrations. These are some experimental cells over there. Usually submerged aquatics are used. This is another picture from these stormwater treatment areas. There are 2 major species, Nias guadalupensis and Ceratophyllum demersum. This is the picture from the past on the left, and then in the situation in 2012 and so on. So you can see that there is much less phosphorus concentrations in these water conservation areas, because here this orange part, this is the part where the runoff is created and flows south to the water conservation areas. And you can see that there is much more concentration, these green circles with less than 10 micrograms of phosphorus, which should be the background concentration. And this is the goal which should be achieved there. So you can see there is a big change between these two periods, mostly because of installation of these dark blue stormwater treatment areas. So this is really a very good example of the use of wetlands to remove, in this case, phosphorus from agriculture runoff. Another picture is from Sweden. And as you may know, the south of Sweden is very flat and very agriculture. So those are the wetlands which treat agriculture, drainage. And Sweden is well advanced in this sense. They have built more than 1,500 constructed wetlands with the total area of more than 50 square kilometers in the South Sweden. And the major reason for that is the eutrophication of Baltic Sea. There is all countries which surround Baltic Sea, like Denmark, Sweden, Estonia, Finland, Germany, Poland. They try to decrease the load of nitrogen, which is mostly coming through agriculture drainage in the form of nitrate. This is another example of agriculture drainage wetlands from Italy. This is from Spain. This is from New Zealand, so it's the southern hemisphere. In New Zealand, there is a lot of pastures because they have a lot of sheep, a lot of cows, and they very heavily fertilize the pastures, which result in a high concentration of nitrate in the drainage waters. So they build this constructed wetland to protect this Lake Ocaro. And this is the wetland with the plants. So that's, of course, the first picture was without the plants. Now it's well planted. Another example from New Zealand. In fact, the New Zealand is well advanced in the use of constructed wetlands to treat agricultural drainage. They have very nice guidelines. And in this case, they are using, this is the drainage ditch. The water is diverted into a constructed wetland, in this case planted with Typha domingensis, and it flows back into the channel. And of course, there is we can see retention more than 800 kilograms per hectare per year. So this is a quite good removal. And they actually come up with this graph which shows that this is the percentage of area of the wetland to the area of the watershed. So if we increase the area of the wetland up to 5%, then the removal is increasing, but then actually start to slow down. So it's probably not wise to make it more than 5% of the watershed area. And here is the link which could be used, and you can freely access this very nice and very detailed guidelines how to design, build, and operate constructed wetlands for agricultural drainage. Here are some numbers. This is based on my survey from 41 free water surface constructed wetlands. It's needless to say that at the moment, most constructed wetlands which were built to treat agricultural drainage are those with free water surface. There's a lot of wetlands in the United States, but also, as I mentioned, North Europe with Sweden, Norway, Finland, but some other countries are involved as well. And so some wetlands could be quite large, you know, for European scale, it's quite large, 150 hectares. As I say, the ratio is from really very small, from 0.0023% to 7.5%. And importantly, the removed load, the mean is about 1,300 kilograms nitrogen per hectare per year. Most of the nitrogen is the form of nitrate. And the same can see for phosphorus. And again, this is from United States, Sweden, Norway, Finland, and some other countries. And here is the mean is about 155 kilograms of phosphorus per hectare per day. So roughly said about 1,000 or 1 ton of nitrogen per hectare per year and 150 kilograms of phosphorus per hectare per year. Here is the graph showing based on these results that really it's not necessary to increase the this ratio. That means the wetland to catchment ratio, and usually 2 to 3, maybe 5% is enough. And if you increase it more, it doesn't bring any substantial increase in removal. Now I would like to present 3 case studies from the Czech Republic, which we have done at our university. And first case is the use of vegetated drainage ditch to remove nutrients from a drainage impacted stream. And this study was done in 2015 and 2016. It's been a quite commonly used technique, especially in the United States, to let the drainage ditches get vegetated, and then the ditches have a very good removal efficiency. Otherwise, if you have just a stream or channel with no vegetation, the water just flows through, and there is no high, sometimes not at all, any treatment effect. So just the basic information, the ditch was 200 meters long, and the maximum flooding area was about 360 meters. So that means that it's about less than 2 meters wide. And there were 3 major species naturally growing: Phragmites australis, Lyceria maxima, and Typha latifolia. Those are very common wetland plants which grow in the Czech Republic. So that's very, very simple. So this is the ditch. Here is the example. This is Lyceria maxima, and this is Typha, which grew really very nicely up to 4 meters. And this is a Phragmites section during the summer. And this is the section during the spring. But the Phragmites is very distinct because the stems usually don't fall down during the winter, so they stay upright, and so you can very easily recognize them on the landscape. And here are the results. So those are from 2015 and 2016. So we achieved in 2015 38% removal, in 2016 53. The concentrations were not exactly high, but because there is a drinking water reservoir nearby, so we are glad that we achieved some removal. As you can see that this is nitrate nitrogen, so that again, most of the drainage water nitrogen is nitrate. So we achieved about 40% removal. We got about 50% removal of total phosphorus, and we have a very high removal of suspended solids. This is quite common that these ditches, they can retain, because the vegetation is very dense, so they are able to retain a large amount of suspended solids, which can get into the drainage water as well. Here there are some numbers. So the average removal of total nitrogen was about 1,100 kilograms of nitrogen per hectare per year. So it's very similar number to numbers I showed you before for the literature survey. There was a slight increase in 2016. And again, you see that most 800 kilograms comparing to 1100, so like 70% maybe of the nitrate, of the nitrogen was in the form of nitrate. And here is the relationship between the water temperature and the removed load. So it's quite nice, but of course it's very much expected because the nitrification is dependent on the water. But the drainage ditch was partially fed also by a small pond where they released the water from the bottom. So it was about 4 degrees. And so even during the very cold periods, the temperature was not so low. So we can see that even in December or January, February, we did achieve some removal of nitrogen. So that was quite encouraging. And this ditch actually never got completely frozen. So there's always been a flow. And this is the removal of phosphorus. So here you can see there is not much relationship between removal and temperature, and the same is for suspended solids. And this is more for suspended solids. It's obvious it's mostly only sedimentation, which doesn't depend too much on the temperature. And the same we can say for phosphorus removal, because there are not so many biological processes involved in the removal, with the exception of plant uptake, which of course during the winter does not exist. But we achieve a very similar removal, about 140 kilograms per hectare per year. As you remember, I said that was the average from the literature survey was 155. So it's very common, but extremely high removal of suspended solids. But this is when we check the literature data, this is quite common. Also, the reports from Sweden, they report between 20 and 30 kilograms, 30 tons of suspended solids retained in the constructed wetlands, or in this case, vegetated ditches. So this is really very, very high retention of suspended solids. So we also follow the BOD5 and suspended solids. So you see that the concentrations are not extremely high for BOD, because these drainage waters are usually not so high in organics. Also, the concentration of suspended solids, they reach 60 milligrams on the average, but there was a very high fluctuation. It's also typical for these drainage waters, and the outflow concentrations were really very low. Then we also did some studies on the biomass. So you can see the dry biomass was by far the highest for Typha, but because they're really huge plants, 4 and 5 meters tall. Lower biomass for Vymazal and lower for Glyceria. And here are the phosphorus standing stocks. That means the amount of phosphorus or nitrogen in this picture, which are sequestered in the above ground biomass per square meter. So this is usually mostly, this is always affected by concentration and the biomass. But the biomass is more important. So no wonder that Typha has the highest standing stock. So you see up to 90 grams per square meter of nitrogen can be sequestered in the plants and subsequently removed if we harvest the plants. And this is the potential if we calculate how much actually we can remove. In terms of nitrogen, it's about, let's say, 25% of the removed nitrogen could be ascribed to plant uptake. And for phosphorus, it's a little bit lower. It's roughly about 15% on the average. So we can remove some phosphorus and nitrogen. It's not the major process, but we can remove some phosphorus. Case number 2 was down about 100 kilometers south of Prague, and we had there was a roughly 0.15 hectare, and we had 3 dominant species: Phalaris arenacea, Carex nigra, and Scirpus sylvaticus. And this is the wetland. It's natural wetland along the stream, which is here, and this is the stream in 2014. So it was very much full of sediments, a lot of some branches, and there was the stream bed was quite full. So during the high flows, the water went overland and went through the wetland. In 2015, we cleaned the stream bed, so there was no overflow during the year. This was the stream, and this is the wetland we looked at. So the water was the year round was below the surface, and there was no overland flow. And what we did in 2016, so this is the aerial picture. This is the stream. So what we did, we put the dam over here. We filled in the drainage ditches which were there, and the water was forced to flow through the wetland and was returned by the last drainage channel. So then we built this structure. I had to close it. Finally, we close it, and then we managed to get the water flow instead through the stream beds through the wetland. So this is the wetland in the spring. This is how it looked like during the summer. So this is the Phalaris arenacea, which formed the majority of the vegetation over there. So we got 2014, where the wetland was flooded only occasionally during high flows and very irregularly. In 2015, there was no flooding throughout the year, and in 2016, there was permanent flooding throughout the year. And here are the results. So nitrate removal. This is the occasional overflow, removal 90%. There is no flow, so this stream was like 200 meters. There was no chance to get any kind of treatment. And when we had the permanent flow, we achieved about 45% of removal of nitrate, and very similar numbers are for total nitrogen. 16%, 0, and 38. In terms of phosphorus, so it's very similar, 38, 5, 40%. And a very big difference is in total suspended solid. There was slight removal in 2014. There was more or less no removal in 2015 when the water was below the surface, and 67% removal during the period where we have a permanent flooding and the water was directed into the wetland. Also, we have this number. So again, the average removal was about 1,100 kilograms nitrogen per hectare per year. More or less everything was in the form of nitrate, and we have the very good relationship between water temperature and removal. But we still achieve the some removal during the cold months of the year. And very similar pictures for phosphorus. So there was about 190 kilograms per hectare and nearly 10,000 kilograms suspended solids. And there is no relationship between the temperature and the removal load. It just usually connected with the flow. We did some samplings for plants as well. And this is the biomass. So you can see it's a very interesting, when there was no overland flow, the biomass of all species decreased very much, especially for Scirpus. Then if you see that if we flood it completely in 2016, the Scirpus sylvaticus nearly disappeared. On the other hand, for Phalaris and Carex, it was a beneficial effect. So they really grew more than the two previous years. And here is again how much we can retain in the plants. So this is nitrogen. So, well, as I said, the standing stock is usually affected by the biomass at most. So there, with the higher biomass, we can achieve higher removal. So for nitrogen is about 40 grams per square meter, and for phosphorus it's about 4. It's usually phosphorus standing stock is usually 10 times smaller as compared to nitrogen. So we can remove some nitrogen and phosphorus through removal. Again, here you can see this is about 30% of nitrogen out of total removal, and about 18%. So those are very similar numbers as for vegetated ditch, about 35% of nitrogen and 15% of phosphorus out of the removed nitrogen and phosphorus can be removed by plant harvesting. And then this is a case 3, which is still actually going on. This is an area which are about 150 kilometers southeast from Prague. It's a watershed of about 16 hectares. Out of those, 10 hectares is under tile drainage. It's relatively higher. It's a low mountain area. The major crops are corn, wheat, and barley, sometimes potatoes. And we started the construction in 2017, and the monitoring period officially was until the end of 2020, but we monitor after the project was finished. So this is the tile drainage quality because the Institute of Soil Research have been doing measurements even before we started. So we have a long-term data. So there's a relatively low organic carbon, 5 milligrams per liter. Nitrates are usually 60 milligrams on the average. They are usually much higher during the spring. It's usually 100, 150 milligrams per liter even. And you will see once we actually recorded 600 milligrams per liter. There's actually a very low phosphorus, relatively low phosphorus concentration. And that comes from the fact that at the moment, the farmers usually use very low dosage of phosphorus fertilizers if they use it. And if they use it, they usually use 10 to 15 kilograms per hectare. So it's much, much lower as compared to nitrogen, and pH was about neutral. So, and design flow for these wetlands were 0.1 liter per second. And so here's the general picture of one of the wetlands. And so here is some few pictures from the construction. Those are wetlands with subsurface horizontal flow. This is April 2018. This is June 18 when we planted. We planted it with bands of phalaris on the right and Lyceria on the left. We choose these plants because they grow quite fast as compared to Phragmites, because here Phragmites, it takes 3 to 5 years before it gets really mature stand. And this is the overall situation. This is the retention pond in case of high flows. Here's the inflow, and there is a constructed wetland 1, 2, and 3. So here are the wetlands in 2019. They are about the same size. They are not exactly the same size. So this is 80 meters, 85 meters, and T3 is nearly 100 square meters. As I mentioned, there are the bands of Lyceria and phalaris on the right. The wetland number 1 and 2, they are filled with gravel, 4 to 8 millimeters, and wood chips, 10 to 1 ratio. And because we try to get at least some difference, so the CW1 is with 10 centimeters above the surface. So there is a combination of surface and subsurface flow. The outlet is at the bottom. And the second one is a very typical subsurface flow compared to wetland. And in the third wetland, we have 80 centimeters of gravel and 20 centimeters of wood chips on top of that. So there, the wood chips and the gravel are not mixed together. The reason why we added wood chips is to provide some organic carbon for denitrification, because, as I mentioned, 5 milligrams per liter is really very, very low concentration as compared to concentrations of nitrate. So this is 2020, and here are these wetlands in August 21. So this is 1, 2, and 3. So they are more or less fully grown. Here's on the left side is Glyceria. On the left side is Phalaris. So you can see still they do not encroach to each other too much at the moment, but probably we will see which plant will encroach to the another. And here is so we have the flow and precipitation. So it's widely varies. And here I have the general picture. We focus mostly on nitrate. We do have automatic samplers. We do have automatic flow meters, which provide measurements every 10 minutes. So there are a lot of numbers. So we just here, we in this from August 2018 to December 2020. Sorry, it should be, sorry for that. It should be extended to the end of 2021. So it's nearly 180 samplings. So the red line, the black line is the inflow, and these three color lines are the wetlands. So here is about 93% of total nitrogen is nitrate. And here you can see is this very interesting, because this is quite typical for drainage. The higher the flow, the higher the inflow concentration, because the high flows, they usually wash out the nitrate from the soil. And also the higher the flow, the higher the inflow load. So this is very much different as compared, for example, to wastewaters, to sewage, where during the rain events, the wastewater is very much diluted, but this is not the case. We have a high concentrations and the high flows at the same time. And it's quite clear from these pictures. So you see that in 2018, we have very high removal percentage from 75 to 93%. In 2021, it decreased to 30.6%. However, if you go to the bottom, you can see that 2021, the flow was about 7-8 times higher, which result it's much higher removal of the load, because we went from 1600 to 100 and 900. So it's very much, very much difference. And if we look out of those, generally plants can take up between 300 and 600 kilograms of nitrogen per hectare per year. So this is, when you compare it to these numbers, so this is somewhere around 10%. And these two figures show the relationship between inflow load and the remove flow. So the higher inflow, the higher remove flow. And this is interesting graph which shows the relationship between flow and removal. So the higher the flow, the lower the removal as percentage. When we compare inflow and outflow, and the red is the relationship between the flow and the remove load. And you can see that it goes straight up. So the higher flow, the lower percentage of removal and higher removed load. This is quite important. And this is very different as compared to sewage, as I said, because in the wastewater, in the treatment of the sewage, when we have the dilution by rain, the concentrations are going very much down. So here we have the remove flow. There are two numbers in grams per square meter per day. grams per hectare per year. And here I marked the red dashed line. The blue dashed line shows the average. I more or less calculated from the 43 water surface constructed wetlands worldwide. And these red lines, they are from the study from Denmark, where they, in the University of Aarhus, they have been doing this for maybe 10 years already. And they have subsurface flow constructed wetlands as well. And their removal were between roughly between 6,000 and 8,000. So this is what we actually achieved in 2020 and 2021, where the flows were much higher. So this is very important. So that's the higher the flow, the higher the removal. Here, when we have a very low flows, we achieve barely 2,000 kilograms nitrogen per hectare per day. But once the flows went up, the removal went up as well. Here is a potential of plants for nitrogen removal, data from 2020. So this is the standing stock. It's still a little bit lower because Lycaria and Palare, they are not as productive, for example, as Typha or Phragmites. So the standing stocks are a little bit lower. So those are numbers. Above the bars indicate the amount of nitrogen in above ground biomass as percentage of the removed amount. So as I said, we can remove some, but this is not the major tool for removal. Just a few more graphs. This is quite important because it shows that in the very beginning of the experiment, the leaching of organic carbon for butchers was very high, and probably, not probably, but for sure, exceeded the amount of organic carbon which was used for denitrification. However, let's say 1 month, the concentrations really dropped down, and at the moment they are very much comparable with the inflow. So you can see that inflow in 2018 was 3.7, and at the outflow there was substantially higher concentration. In 2019, the concentrations dropped down, and at the moment we can see a very slight increase for, let's say, 7 milligrams per liter. We have 10, 8, and 9 milligrams. So there's a very slight increase, but this is not so bad. So to wrap it up, we can say, based on our experience, on the field experience, that the removal of nitrogen in experimental stage of stream wetlands and subsurface constructed wetlands averaged about 1,100 and 6,000 kilograms per hectare per year. So it seems that the subsurface flow constructed wetlands are more effective in removing nitrogen, and that's because the subsurface flow constructed wetlands, they provide very good conditions for denitrification. Denitrification in the surface flow constructed wetlands is a little bit limited because most of the water column is aerobic, so it's not suitable for denitrification, and denitrification usually occurs at the bottom layer of decaying vegetation. Removal of phosphorus in our experiments varied between 140 and 190 kilograms phosphorus per hectare per year, also very much comparable with the literature data. We didn't follow too much phosphorus in the last study because the inflow concentrations were very low, and also that was not a big problem. In terms of plant removal, it varies between 1 to 36 and between 12 to 19% for nitrogen and phosphorus. So it's, as I already mentioned, we can achieve some removal Of course, if we select plants which can be harvested several times during the year, so then maybe we can achieve higher removal. But then we also have to select the proper plants. As I mentioned, we selected in this last case flowers and mycelia because they grow relatively fast, and the project was for 3 years. So we tried to achieve some good biomass before the end of the project. In case if we put pragmatics, we probably will not achieve. But indeed, in the long-term perspective, like 3, 4, 5, 6 years, the biomass of fertilizer will be much higher, and also the standing stock. It means will be higher, so we can remove some more phosphorus and nitrogen. It's very difficult to say, at least under Czech conditions, whether they meet requirements, because there are any legal limits on discharge of agricultural drainage waters. There are no limits. Therefore, it's difficult to say if they meet the requirements. But the results show that the wetlands are able to remove relatively high amounts of nitrogen and phosphorus. And our results more or less confirm what has been reported in the literature. But usually in the Czech Republic, the water authorities, they always want to get the proof in our country. So they say, well, we understand it works in Denmark or Austria or France or United States, but we should prove it here. So therefore, we actually established these experiments, and we came up with more or less the same result, which is satisfying. So quite important is that we think that to evaluate the effect or effectiveness of these constructed wetlands for removal of nitrogen and phosphorus in terms of percentage, that means the comparison between the inflow and the outflow, is usually not appropriate, because much more important is the load removal. That means the grams or kilograms or tons per year, because this is always affected very much by flow. Also, the role of plants in terms of nutrient removal through nitrogen and, of course, and phosphorus accumulation is strongly dependent on the inflow load, because the amount of nitrogen and phosphorus in the plants are usually very much similar. And of course, then it depends on the inflow load. The higher is the inflow load, the lower is the role of plants, because there is a more or less certain I would say, limits for nitrogen and phosphorus can be uptaken by plants. And if you increase the load, then we do not increase the accumulation. So if we have a very lightly loaded systems, then we probably can achieve very much higher effect of the plant removal. I think that we also showed that relatively simple solutions like vegetated ditches or off-stream wetlands may provide a very similar treatment or removal efficiency as constructed wetlands for removal of nutrients. Because, for example, the vegetated ditches, they are actually very, very cheap to build. They, of course, you can let them overgrown spontaneously, or you can plant some species there to increase the plant biomass, and it's relatively simple. The problem, little bit, at least in the Czech Republic, is that according to the law, it's a very old law from the 1950s, the drainage ditches should be flow-through. That means that you actually should not let them overgrow, because then they are not flow-through and they should be cleaned So now this is a debate whether this law is still, I would say, efficient, or if this still should be kept in effect. And in general, I can say that all studies, both from the literature and also our studies, show the very high efficiency for nutrient removal from tile drainage or streams, small streams, which are impacted by the tile drainage, because you cannot treat the big streams. But if you have a small streams, especially in the upper reaches, then it's possible to treat the whole stream, and with relatively very cheap operation and maintenance costs. Of course, there are some investments costs, but if you have the wetland somewhere in the middle of the field, then it will be very difficult to build some conventional treatment plant where you probably need some electricity. So this is the very effective and very useful tool how to treat agriculture drainage. So thank you very much for your attention. And I'm not sure if I should go to chat and answer the questions. I will go.
Thank you very much, Dr. Vymazal. We do have a few questions, and we're about out of time, so that's about what we have time for. But the first couple of questions we have regard the actual maintenance of the constructed wetlands, and the first is, how frequently do you suggest harvesting vegetation for best performance?
Well, it depends on the plant, because some plants can be harvested repeatedly. For example, Phalaris aluminacea could be harvested 3-4 times a year, and it doesn't make any damage to the stand. On the other hand, Phragmites australis, at least under our conditions, could be harvested only once, very late in the season, because Phragmites shifts the storage nutrients very late in the fall. So if you cut it throughout the vegetation season, it's the best way how to kill the stand. So it depends on the plants, and of course, if there is a chance, so probably the more harvest you can perform, the better. And of course, if you have some lightly loaded systems, then the harvesting could be very effective.
Thank you. Also, do you replant following the harvest, or are the roots removed, or do you prefer cutting the plants and leaving intact the roots?
Yes, this is probably a little bit a question, because it is believed that in the very beginning of the performance, the major source of organics are the wood chips, which are part of the filtration material. But over the years, the wood chips will be exhausted, and the organic matter will be provided through the decaying plants. So maybe it would be effective not to cut it completely and leave some plant material for decomposition and release of organics. But in the very beginning, when you have enough organics from the wood chips, or maybe some drainage waters may have organics enough to support denitrification, then it's possible to harvest the plants at the base. What we actually do, for example, in constructed wetlands for sewage treatment. So if we harvest it, we cut the plants at the ground.
Thank you. Final question. We have a few more popping up. Let's see if we can get through these. Have you used similar wetland treatment for petroleum wastewater treatment, such as heavy metals, petrochemicals, and others?
Well, we don't have petroleum wastewaters in our country too much. We have some refineries. However, there are some very fine examples of constructed wetlands which were built to treat wastewaters from the drilling sites. I think that the best known is that in Oman, where is a wetland about 4 square kilometers planted with phragmites, and they combine it with evaporative ponds. So they, at the end, they do not have too much inflow and they use it for irrigation. But in general, the petroleum wastewater are not so difficult to treat because they usually contain organic compounds which are not so difficult to degrade. So there are some good examples of treatment. And of course, in case of heavy metals, we have done a lot of studies in the real systems, and it seems that the major retention mechanism is the precipitation in the sediment. And mostly, especially in the subsurface flow horizontal wetlands, there are anoxic or anaerobic conditions. So we quite often have reduction of sulfide, which produces hydrogen sulfide, which very quickly reacts with heavy metals and bind them as insoluble sulfides. And they mostly stay in the sediments, and there is relatively very low translocation to the above ground biomass. So even if the concentrations of heavy metals are a bit elevated, you don't need to worry about increased concentrations in the above ground biomass. So you can cut it and you can harvest, you can put it in the compost, or well, it's usually usual way is to burn it. But heavy metals usually stay below ground.
Cool. I like that part about the metals. There's a follow-up question regarding replanting. Did your nitrogen and phosphorus measurements only include above ground biomass? I didn't notice if you told us during your presentation. Thank you.
Yes, we measured only above ground biomass because, you know, if you, well, you can test the below ground biomass as well, but if you really want to harvest it, you would probably destroy the whole wetland. So therefore we, you know, from the natural stance and from some studies we did in other constructed wetlands, we know that the amount of nitrogen and phosphorus is about the same above ground and below ground. But because, you know, this is the subsurface flow system, so it's not, you know, not possible to harvest it completely. For example, if we had a floating islands, these floating treatment wetlands, then we can very easily harvest it, the roots and rhizomes. I don't want to say below ground because it's floating in the water, but you can harvest also the roots and rhizomes, and then you would probably increase very much the removal through harvesting. But then you should either left some plants in place or you should replant it if you remove also the roots and rhizomes.
Thank you. And one more question. Can the use of reactive media enhance the removal efficiency of the nutrients?
Reactive? I don't understand. Reactive?
I think that would be like, you know, like plastic balls or something like you'd use for, you know, in an aquarium.
Yes,
filter.
well, there are many types of filtration materials which are used especially to enhance phosphorus removal, because if we use a very conventional gravel or crushed rock, they usually do not have very high absorption capacity for phosphorus. So there are different materials to enhance phosphorus removal, and plants usually grow quite well. So, well, yes, I think it's possible, but because the phosphorus is mostly retained by absorption, so then we can probably expect that the absorption capacity will be exhausted and we will have to replace it. So it means that it will be difficult. For example, in Denmark, what they do, they are using these constructed wetlands with surface flow, is sometimes subsurface flow, and they have a special, like a tertiary treatment. They have filters with, they call it sand shell, which is sand which was created by crashing shells in the past. So it has very high capacity because it contains a lot of calcium, and they have like a special cartridge, so they can actually take a crane and take it out and replace it. But if you have it in the filtration bed, then you will have to probably replace it, and then you will have to start again. But to your basic question, yes, it is possible to use some other filtration materials. It is possible.
Thank you. Well, that's probably all the time we have for questions. If you have any more questions for Dr. Vymazal, his email is up on the screen there, and will be available if you wish to go back and review the presentation on YouTube. With that, I'd like to thank you all for attending, and especially you, Dr. Vymazal. That was an awesome presentation. Thanks so much for being with us. Thank you for our sponsors, and please be certain to visit their websites and see what they're all about.
Thank you very much for the invitation to have this presentation, and indeed feel free to contact me, and I will be happy to answer if I know the answer. So anyway, feel free to contact me. Thank you very much.
Thank you. And don't forget to complete the survey afterwards, and be sure to check out the upcoming webinars.
Thank you. Bye-bye.
Bye-bye.